Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy instructor at Foothill College in Los Altos Hills in Silicon Valley, and it's my great pleasure to welcome everyone here in the Smithwick Auditorium and everyone listening to us or watching us on the web to this lecture in the 13th annual Silicon Valley Astronomy Lecture Series. This series, 6 times a year, brings distinguished astronomers from around the Bay Area and the country to tell us about the most recent and exciting developments in our exploration of the universe. The program is co-sponsored by the Foothill College Astronomy Program, a community college here in Silicon Valley, open to not only college-age students, but to everyone who's interested in learning, by the SETI Institute, the Search for Extraterrestrial Intelligence Institute, which does both science and public education about the search for life in the universe. NASA's Ames Research Center, one of the premier NASA facilities right here in Mountain View, California, and the Venerable Astronomical Society of the Pacific, an organization founded in 1889 to do what this lecture series does, to bring information about astronomy to the wider public. This evening's Silicon Valley Astronomy Lecture is by one of my favorite speakers, Dr. Dana Backman. Dr. Backman is the Director of Education and Public Outreach for the project we're going to hear about, the SOFIA project at NASA's Ames Research Center. He's also an adjunct professor at Santa Clara University and at the Stanford Continuing Studies program. Before joining the SOFIA team, Dr. Backman was professor of physics and astronomy at Franklin and Marshall College in Pennsylvania. He's the co-author of 3 really wonderful college-level astronomy textbooks explaining astronomy to beginning students, and a frequent public speaker, not just on the SOFIA program, but on astronomy in general. His research specialty is infrared astronomy, the study of the universe by collecting heat rays, and that's exactly the kind of work that the SOFIA telescope is designed to do, and exactly the kind of work he's going to describe tonight. There'll be a special announcement at the end for teachers, so stay tuned for that. But for now, it's a very great pleasure to introduce Dr. Dana Backman speaking about astronomy from the stratosphere, NASA's SOFIA mission. Please welcome Dr. Backman.
Okay. Can you hear me okay? Yes, all right. I won't do the can you hear me in the back gig. Andrew Fracknoy got me my first local speaking gig in 1989 in a series about the Drake equation and the search for life in the universe up at San Francisco State. So it's always nice to work with Andy. So thank you. So as Andy said, I'm in charge of the education and public outreach programs for SOFIA that you see here, and the blurb for the talk expressed the question, why would someone do this? Why would you take a used commercial airliner and chop a hole in it with a garage door over that, put a 17-ton telescope in the back and expect anything good to happen from that? Well, NASA and the United States, as well as Germany, you see that's the German Space Agency's logo, DLR, there. So it's a 20% German and 80% US project. And it's really just getting going. The first science flights were in December 2010. So we're just 2 years along of what's hoped to be a 20-year mission. And the mysterious blob on the left is an infrared image of the ring of gas around the black hole, supermassive black hole at the center of the Milky Way galaxy that SOFIA took a year and a half ago, and we just released at the American Astronomical Society meeting in Long Beach in January. So I'll come back to what you're seeing in that image, but believe me, if you look at the center of the galaxy with Hubble, you don't see that, only with SOFIA. So my outline is a little bit of background information about the context and why we're doing this, and then the history of SOFIA and its present status, how we're doing. SOFIA's science, the kind of things that SOFIA is particularly cut out for relative to other space observatories or ground-based observatories, and then the SOFIA's Airborne Astronomy Ambassadors. That's what Andy was referring to in terms of a special treat for teachers. So remind me to do that. Here, this is a cartoon of something that actually happened. William Herschel was the person who in, I think, 1778 had discovered Uranus, the first person to discover a planet. The other planets are, the closer planets are naked eye objects and have been known since antiquity. But William Herschel, scanning the sky, found a disk that moved, and it was the planet Uranus in 1778, and then he named it George. Actually, Georgium Sidus, George's star, and you can probably figure out how the paycheck issue was connected to that. Actually, he started life in Germany and moved to England, and for a while was a classical composer, and you can hear his chamber pieces on KDFC once in a while, and picked up a book on the mathematics of music that he thought was so wonderful that he then read another book on the mathematics of astronomy by the same author and became an astronomer, and in fact one of the premier astronomers of the last several centuries. Discovered Uranus. His sister Caroline was his observing partner. Doesn't get enough credit, of course, for her part in this, but that's their monster telescope in the backyard there, which the window would not have been open for this particular experiment. But anyway, wiser heads prevailed, and George's star got renamed Uranus sometime later. The French in particular were not impressed by naming a planet after the king of England, so in France it was called Herschel for 10 or 20 years. Well, anyway, so what he's doing in this picture, he has a board with 3 thermometers. That's the most sensitive instrument he could have at the time to measure the strength of sunlight. And so he's got sunlight coming through a prism on the wall of his laboratory and coming as a spectrum onto the table. And he's moving the thermometers around to try and compare the intensity of the different colors of sunlight, their efficiency at heating the thermometers. He's got one outside the sunlight as a control, so he knew what he was doing. He's got 2 inside the sunlight beam because it's, measure twice and cut once philosophy. 15 would be better, but 2 is good. And at this moment pictured here, he has pushed the thermometers past the red, and the thermometers are still feeling sunlight, and the human eye doesn't see anything. So there's a color beyond the red, like the Dr. Seuss book, On Beyond Zebra. There's a color beyond red that the thermometers treat or detect as well as the colors that we can see, but the human eye isn't seeing those. And he named it, the word infrared is his coinage, meaning beyond red or below red. Now, if you're really thinking, you might be wondering, why didn't he discover ultraviolet that same afternoon, just swing the thermometers over the other side? The answer is that ultraviolet doesn't get through the glass prism, and not much of it really gets through the atmosphere. Luckily for us, the Earth's atmosphere is almost opaque to ultraviolet, and so we can go outside without dying of sunburn. But anyway, he discovered ultraviolet. He discovered infrared, and ultraviolet waited 20 years to be found. But this is the discovery of what may sound oxymoronic, invisible light in the year 1800. And now astronomers, when they can use infrared detectors to look at the universe, it's a completely different universe with an infrared camera than it is with an optical light camera. On the left is an image with a camera that's seeing the same wavelengths of light that human eyes see. On the right is a composite of data from the IRAS infrared space telescope that was working at a wavelength of 60 microns. So infrared astronomers think in microns. The human eye sees from 0.4 to 0.7 microns. So this image on the right is at 60 microns. You're seeing interstellar material, the glow of the gas and dust between the stars. And the bright white and yellow regions are dense clouds in which stars are forming. And they show up like gangbusters in the infrared image, and they're not apparent in the optical image. In the optical image, you're seeing mostly empty space and things like the temperature of the sun, a few thousand degrees, a few tens of thousands of degrees. Here you're seeing things in space glowing at 50 Kelvin, 100 Kelvin, several hundred degrees below 0 Fahrenheit, but still giving off radiation. They're above absolute zero. So unless you have both of these pictures and maybe a few more at other wavelengths, you don't have the whole story about what's going on out there in the universe. In the 200 years since Herschel, we've found that there are a whole spectrum, a variety of types of radiation, which it's fair to call light. All of them you can call light. It's the same kind of wave. They all travel at the so-called speed of light. And to mix metaphors a bit, if this was an 88-key piano, we're only detecting with our sensory apparatus 4 keys in the middle of 88 keys. The rest of it is we need instruments to pick up. So gamma rays, X-rays, ultraviolet, visible light, this little narrow window, infrared, microwaves, and radio waves. The divisions are arbitrary. There's nothing in nature that says you need to call this one thing and this something else, or this one thing and something else. These names come from how we make them and how we use them. They're all the same kind of wave. They're just higher frequency or longer wavelength or whatever. Quantitatively different, but not qualitatively different. So now we know all of those. And NASA embarked on a program to put telescopes into space that would detect in each of these bands. So there was a gamma ray observatory, initially labeled GRO, and the X-ray, AXAF, Hubble Space Telescope. Basically its instruments see what the human eye sees, those wavelengths, plus a little tiny bit into the infrared, a little bit into the ultraviolet, but basically human visual wavelengths for Hubble. And SIRTF, SIRTF, the infrared space telescope, NASA has a policy now of calling them by acronyms before launching them, and once they're up and working, then you name them after somebody famous. So Compton, Chandra, Hubble, and Spitzer are the names once they were up and going. Hubble used to be called the Large Space Telescope, LST. So Chandra is still working, Hubble is still working, and Spitzer is sort of limping along on half of one of its 3 detectors, but it's still flying and so on. What these observatories see by concentrating on different parts of the electromagnetic spectrum, they see different temperature material in space. An X-ray observatory sees stuff in space that's 1,000,000 degrees. Hubble sees things that are 1,000 or 10,000 degrees like the sun. And Spitzer sees things cooler than Hubble, like stars that are forming, planets that are forming, and the raw materials for stars and planet. So, to roughly speaking, they're seeing different temperature regimes. These are seeing cosmic catastrophes. These are seeing planets and stars in formation down there. And Hubble is seeing mature stars. Actually, here's a better illustration of that. This is a composite from the Chandra X-ray Observatory, from the Hubble Space Telescope, and from the Spitzer Space Telescope, all of this galaxy, Messier 101, pinwheel galaxy. So here you see stuff that's 1,000,000 degrees. Here you see stuff that's a few thousand degrees. Here you see stuff that's a few hundred degrees. This is the end points of star evolution. It's supernova remnant clouds and accretion disks around black holes and all sorts of that exciting stuff. These are mature stars perking along in the middle of their lives, and this is the raw material for new stars. So if you put them together, you have a life cycle, an ecosystem of a galaxy. And you wouldn't have that if you didn't have all the pieces here. So you're getting a picture now of how SOFIA, which is an infrared observatory seeing much of the same range of wavelengths as Spitzer does, it's more concentrated on the youth and the formation of stars and planets than it is at the end stages of life. But that's not completely true, but it's a good first shot at it. So here, however, so the infrared tells you all sorts of interesting things if you can observe it, but this is a graph that shows how opaque the Earth's atmosphere is versus wavelength. And this is X-rays and ultraviolet. This is the visible light, which does get through, because then we can see the sun and the stars. Infrared is mostly, not completely, reduced, so Herschel was just detecting a small part of what's hitting the Earth's atmosphere. Here's the radio window, so you don't need a radio observatory in space. Those work okay on the ground. Radio waves reach the surface of the Earth from space. So you've got these two windows, and most of the rest of the universe is blocked. Infrared, in particular, is blocked by water vapor. Water vapor is a greenhouse gas, and you can see that it's the same thing. Whether the energy is trying to come in or the energy is trying to go out, the water vapor blocks it. This is an expression of that idea. This is a thermal infrared image of Earth from a satellite in geosynchronous orbit, and you're not seeing the surface of the Earth at this infrared wavelength. The Earth's atmosphere is opaque. What you're seeing, the blacks regions are the tops of thunderheads, big tropical storm systems that are cold. This is some very warm tropical air mass, but it's not the surface of the Earth. And I have no idea what piece of the Earth this is. Sometimes I think I'm maybe seeing Alaska up here, but I don't think so. I think this is just an anonymous piece of the Earth. You can't see the surface of the Earth at infrared wavelengths from the outside. You can't really see the universe from the inside. So yet another way to look at that, the stratosphere, the second layer of the Earth's atmosphere, is very dry. Almost all the water vapor is in the troposphere, the layer we live in, the bottom layer, and with the layer that has all the weather and the circulation. If you can get your telescope above the tropopause into the stratosphere, you're most of the way to space in terms of how much infrared you can get. So you don't have to go all the way to have a space telescope to have access to the infrared universe, as long as you've gotten above the water vapor layer. So here's a solution. This is the Kuiper Airborne Observatory that was located was based at NASA Ames. There, it had a 36-inch telescope here and a chamber behind the cockpit. The astronomers and technicians worked in the cabin here. This is parked at NASA Ames. This is the big wind tunnel that's along 101, just seen from the other side. And the offices of the SOFIA crew are in the walls of this hangar building here, which was originally going to be SOFIA's nest, but is not, for interesting political reasons that I might go into. But this fellow here was a Kuiper crewman. There it is, yes, there he goes. I flew on it twice, and you flew on it, how many, 5 years? No, okay. So this is an airborne observatory. It's carrying a telescope into the stratosphere. And worked for more than 20 years, 21 years total out of NASA Ames. So that was not the first infrared telescope in an airplane, but it was the earlier ones. The one before that was a Learjet with a 10-inch telescope fitted to a U-port, to a passenger window. So this was serious science. And the idea of doing this was suggested by Gerard Kuiper, astronomer after whom this was named posthumously. He was Carl Sagan's PhD advisor among his many claims to fame. He was the only person doing serious planetary astronomy for the year, sort of the 1930s, 40s, and 50s, because Percival Lowell, you may know, the scion of the Lowell textile fortune in Massachusetts, set up Lowell Observatory in Flagstaff to go look for the canals on Mars and make maps of them. And by 1930, that was a pretty stinky. The astronomers were not very enamored of planetary astronomy after that. But Kuiper soldiered on for decades, being basically the only planetary astronomer, and suggested that NASA might think about best of both worlds. Get your telescope above the atmosphere, but you don't have to get it all the way into space. So the Kuiper had its career, but towards the end of that, astronomers always want bigger and bigger telescopes. So the idea was that we would buy the biggest aircraft in terms of the body width that we could get and put a larger telescope than the Kuipers in it. And so at NASA Ames, here's the wind tunnel tests for a 7% scale model of SOFIA. You can see that, well, let me go back to the Kuiper for a second here. You'd think you want to put your telescope ahead of the wing instead of behind the wing because it's going to be very turbulent back there, wouldn't you? So this is where you would, your first guess of where to put it. And so the same thing with this, except that look at the complicated shape of a 747, which was the widest body plane we could buy in 1996. The shape here is so complicated that the door would have been so expensive that it was decided to try seeing if you could get away with putting the door behind the wing, and would it be turbulent, too turbulent or not. So these are the tests that showed that indeed you could have the door behind the wing and the telescope behind the wing and you'd be okay, which saved probably hundreds of millions of dollars, I'd guess. And the other, and although I'm told by the chief engineer of SOFIA that for a while they were still considering trying to do it up here, but then the Berlin Wall came down, and as he put it, West Germany had to buy East Germany, so they didn't have enough money to do this what the Germans would consider the right way. So we ended up with the telescope in the back of the plane, and we're fine. But anyway, so there's a little bit of strange history. So now we have SOFIA. It's a 2.5 meter telescope. The primary mirror is actually 2.7 meters, but we only look at the central 2.5 meters, 100 inches of it, in a 747 SP. So if you know your airplanes, you're thinking, that's a short, stubby 747. That's not a regular passenger 747. Boeing built 40 of these for long-distance non-stops, like New York to Tokyo, would have a smaller passenger load because they could get that was the trade-off. Small passenger load, but long-distance flights, and it didn't end up being economically viable. So they made a bad bet, but it's just what we want. There are some of them still in service. Some Mideastern airlines have them, the siblings of SOFIA, but the long-distance 747, and we don't care to first order how big the passenger compartment is. So that's what we have. And the plane is at NASA's facility in Southern California at Palmdale. It's about 60 miles from Los Angeles. Eventually, not yet, we'll get to 120 flights per year. Starting this summer in July, we'll do our first southern deployment and take the observatory to New Zealand for most of a month and work out of the southern hemisphere, work on the southern hemisphere skies. Let's see. Okay, so I'm going to, I didn't put this in here. I didn't embed it in the PowerPoint because I thought actually that was more dangerous than not. Oops, I'm not seeing this on the, are you not seeing my, you're not? Well, you're not seeing that. Okay, you're not seeing a movie, which I would like to show you in a minute. Let's see. Okay, so we're thrashing around. I'll come back to that in the question period. What I was going to show you was the first open door test of SOFIA, which was in 2009. And amazingly enough, we had tested the design and the wind tunnels and so on, but it was nice to know in practice that it was all fine. And the pilot said he could not tell the difference in handling when the door opened between the 747 without a hole and 747 with a hole. We were also concerned that it was going to sound like blowing on a Coke bottle for 10 hours, which wouldn't have been very good. And it doesn't do that either, so this is all good. Let's see. Here's the interior cutaway. So where the passenger seats had been are the workstations for the scientists and telescope operators and so on. Upstairs is the flight crew. There's seating for guests and scientists who are off shift and so on. There's maybe several scientific groups sharing one night's observing. And the telescope is behind this bulkhead here that takes 1 million pounds of pressure when the door is opened. Why is it open to the air and not with some kind of window? We wanted to work all the way from ultraviolet to microwaves, and the only material that would pass all of those wavelengths is diamond, and they weren't going to let us build a 10 by 10 foot diamond window. So this is what you have. So here is the telescope, which is a reflecting telescope, primary mirror, secondary mirror, I'll show that in a second, and the light actually comes through. A third mirror is bounced through the bulkhead in a tube, and the camera or spectrograph that we're using to study the light is located here. That's accessible from the cabin. Nobody goes back into the chamber with the telescope except grad students if we need to. No, I'm kidding. Okay, so here should be light coming from a celestial source, hits the primary mirror, goes up and hits the secondary mirror, bounces off a dichroic that splits the infrared and visible light into two slightly separate beams, and then we pick off the visible light with a TV camera so we can look at the field of view that the infrared instrument is looking at and make sure we're all lined up. So this telescope, 17 tons of it, is hanging on a spherical bearing that's embedded in that bulkhead. So I'm anticipating the question, how do you keep this thing steady? The telescope is floating, 17 tons of it, on a hydraulic fluid layer between two concentric spheres. So when we're operating, it's actually isolated from the high-frequency motions that everyone's familiar with in an airplane. And then we have to do a lot of fancy calculations to point the telescope based on where the star is and where the SOFIA is and where the Earth is. But the telescope has only a small amount of motion in azimuth. So basically, you point the telescope in that axis by turning the plane. So the autopilot is programmed before the flight with the list of objects that the astronomers want to study, and the autopilot's job is to keep the plane out of the way of the telescope. Right? For the pilots are hands-off. The telescope is not flying the plane. That's not how you'd want to do this. In case somebody types the wrong coordinate in, go. Right, but the autopilot is just keeping the door out of the way of the telescope that's actually rock steady in inertial space. As I said, I flew twice on the Kuiper Airborne Observatory, and there's this disconcerting experience standing there watching the instrument flange where the instrument was sticking into the cabin, and it's swinging around and doing all kinds of stuff like this. I say, what's going on? And then somebody explained, it's holding steady. The plane you're in is twisting around a perfectly rock-steady telescope. Right? So now here at NASA Ames, we had the Aluminizing Chamber. This is what we call a hero shot. This is Patrick and Nancy, two of the technicians, taking their own picture in the newly aluminized primary mirror. They're lying on their backs in the bottom of the aluminizing chamber, taking their picture in the SOFIA primary mirror that's hanging reflective side down from the ceiling. Before this moment, they had the chamber evacuated, and then aluminum had been vaporized, and aluminum vapor had been blown on to coat the mirror. And then they open it up and go in and check. And the bunny suits are not to protect the people, but to protect the mirror from people juice. All right, so you've got that. So it's beautiful. And it's holding up well. This is 2 or 3 years ago. So when I teach this intro astronomy class at Santa Clara, the students come in with a preconception, one among many, which is that the telescope is just like a big microscope. It's to make small things big. The small things might be way far away, that's why they're small. But actually, I'm sure you realize, the telescope is to make faint things bright. It's not really doing much magnifying, or you can change the magnification by changing your eyepieces, so it's not an intrinsic property of the telescope. You want the telescope barrel to be as wide as possible, to be as big a light scoop as you can get, to scoop up as much light to make something faint be visible. But there's a second reason why you want a larger, astronomers want a larger telescope, which is that this diffraction is an effect of light waves going down a tube, going past a barrier, a boundary, and down a tube where they rattle around basically and smear the image, and it's unavoidable. Anytime you put light waves down a tube, you're going to get this diffraction smearing that you can't avoid, but it's better the bigger the telescope is. There's less smearing. This is as if you looked at this fellow with a 36-inch telescope, and this is a little fellow with a 100-inch telescope. He's not bigger, but he's clearer. So that's the second reason why you want a larger telescope, all other things being equal. So NASA put out a proposal in a call for proposals in 96, and there were 5 competing proposals to build and then operate SOFIA, and a consortium of universities won that included the SETI Institute and the Astronomical Society of the Pacific, the sponsors of this series, to do the public outreach for SOFIA. So we bought our plane, used from United. It started out as a Pan Am airliner, and then Pan Am sold it to United. And if you flew across the Pacific in the 80s, you might have been on our plane with either Pan Am earlier on or United later on. It was just a commercial airliner. But now we bought it and flew it to Waco, Texas, to a aerospace company called L3 Communications. Their usual business is putting spy gear into Navy planes, but they bid on the idea of putting a telescope into SOFIA. And so here it is actually on its way to Waco, Texas from San Francisco Airport, where it was when we bought it. And it says Kuiper Lindbergh up there, which you might wonder what's so special, why is that? We have a very special airplane, this airframe. This is Anne Morrow Lindbergh on the left, breaking the champagne across our ship's bow in 1977 when it went into service on the 50th anniversary of Charles Lindbergh's flight across the Atlantic. So it served as the Kuiper Lindbergh. It's a historical plane even before it became our observatory. And on the right you see Eric Lindbergh, their grandson, rededicating it, pulling the bunting off of the Kuiper Lindbergh sign. He gave a rousing talk after this. He's on the X Prize selection committee for commercial and private exploration of space, and he said it's not necessarily well known that my grandfather, he said, was motivated as much by the prize purse as by being a hero first to go across the Atlantic in a solo, and $10,000 or $20,000 in 1927. He says, but I kind of got the hint when he'd come around, he'd make my cousins and me, do things like wiggle our ears for a quarter and stuff like that. And he says, Grandpa's the prize purses do motivate people to do extraordinary things, and that was part of his speech. He also reenacted his grandfather's trip for the History Channel. You may have seen that. He flew a private plane across the Atlantic for that. So now here's SOFIA with the telescope primary mirror cell being craned into the fuselage for the first time. And every time I see this picture, I think, that's a single point failure. And how many years of bad luck do you get if you drop a 100-inch mirror? But it went fine, and they put it in there. And then the next slide I have shows 4 of the 7 instruments that we have that actually analyze the light that the telescope has gathered. There's a mid-infrared camera built by Cornell called Forecast. There's a near-infrared camera built by UCLA called FlightCam. There's a far-infrared spectrometer called GREAT, built at the Max Planck Institute in Germany. And there's HIPPO, built, which is rapidly measures the brightness of objects. High-speed photometer built at Lowell Observatory in in Arizona. So these are actually the first 4 instruments that have been on SOFIA. This shows HIPPO actually on SOFIA's mount there. This is forecast on the Mount Palomar 5 meter. Some of what forecast does you can test from the ground, so they took it to Mount Palomar. You can't do that with GREAT. It doesn't work in the lab. So here it is actually on SOFIA's telescope instrument mount. And this is the flight cam up at Mount Hamilton above San Jose being tested. You can do some of those tests there. Now we have other tests of how the telescope is pointing and how all the systems are working that you can perform on the ground. So these are line-ops, that we call them. We're on the flight line with the telescope pointing at some celestial object and just pretending you're flying, see if the telescope can track, that kind of thing. We tend to point at the North Star, so we're not challenging it too much. You don't have to have a tractor pull the telescope around in a circle as the Earth turns. But the hangar where SOFIA lives was the soundstage for the Pirates of the Caribbean movie. That's another part of our mythology here, but true. So here's SOFIA in Palmdale. So SOFIA's, the project is actually run from NASA Dryden, which shares a campus with Edwards Air Force Base, but our German partners were having so much trouble getting through the NASA, not the NASA, the Air Force security process, really they're our friends now, that the decision was made to put SOFIA and a couple of other civilian research aircraft at a facility outside the Edwards fence in Palmdale. So it's 20 miles from Edwards and Dryden, and actually the city airport of Palmdale is where we're sitting now. So here, the first open door test flight, and I will hope that the AV folk, while during questions, if they can come down here and get us to watch the first open door test. There's something pretty cool about that I want to tell you about. But it's over the Mojave, over the deserts of Southern California, where we did those tests. And here was the first flight that where we took astronomical data in flight, May 25th to 26th, 2010, first light flight. This is a little confusing, but this is the coastline of California. These areas off the coast are restricted military flight zones. Here's the international border between Southern California and Baja here, and this is the coast of Baja going down here. So here was how we flew, and remember I said that you have to point the telescope mostly by turning the plane. So if you look at that star, you have to fly this way, and if you look at that star, you have to fly this way. So we zigzag all over the area, determined not by anything on the ground, but by what we're looking at. So this is the flight schedule, and dead leg, it's not as ominous as it sounds. That means this was getting to somewhere but not observing. There was no astronomical observing. So 4 dead legs leaving Palmdale. Then the first thing pointed at, although we weren't taking pictures, we were just trying to line it up, was Alpha SCO, and then a bright infrared star, a dead leg, another bright infrared star, a dead leg, and eventually we got to looking at actually taking images of Jupiter on that night. I'll show you one of those later. So I have a few slides about the kind of science that SOFIA can do. Here are 3 images to about the same scale of the middle of the Great Nebula of Orion, Messier 42, the star-forming region that's in Orion's sword. On the left is a Hubble Space Telescope image, and basically the dust clouds in this star-forming region are opaque. You're not seeing anything. You're seeing the exterior of the clouds. You're seeing light reflected off of that from bright stars in the foreground, so on. You're not seeing inside. With a near-infrared camera, you can see partway into the cloud because the dust is transparent in the infrared, and all those white specks here, not visible to Hubble, but to the near-infrared camera, those are stars forming, hundreds of stars condensing in this cloud in Orion's sword. This is a SOFIA image, and what you're seeing here the dust itself, the construction material for the stars, is the light source. So here you see the cloud reflecting starlight. Here you see the stars embedded inside the cloud, and here you see the cloud material itself as what's giving you the radiation. So 3 different views, put them together before you know what's going on. Well, this next one might be, so this is the one I led off with. What you have here is an image with the Cornell's forecast camera of a region around the center of the galaxy. This ring is about 6 or 7 light years in diameter, and it's rapidly moving, rapidly revolving gas and dust, and the speed with which it's going tells us that right here is 4 million solar masses of black hole, right here. And the white, hot material, it's showing up white in the infrared, are streamers of stuff streaming down and disappearing down the gullet of the black hole. And here's what you see with Hubble. Oh, nobody home. All right, it's some stars. Actually, these stars here are here in the center of this picture. They're not in the foreground. But this material is giving off radiation at infrared wavelengths and nothing at this is near infrared, basically, very near infrared, just over the line from visible light. This is what Hubble sees is a dense cluster of stars at the center of the galaxy, and all the excitement is in that infrared, mid-infrared picture. So here, hiding here is a monster deep inside this cluster of stars. And here we see the results of the monster's gravity, this ring torus of material and this streamers of stuff falling down into the black hole. And this image took 3 minutes with SOFIA to take this. Right? And this might be an hour with Hubble, something like that, maybe in orbit, yeah. So I'm not saying that this picture is, you can get away with just having this, because this tells you how many stars there are there and also about their distribution. So the two together are what you need to understand what's happening in the nucleus of the Milky Way galaxy, which that 4 million solar mass black hole, it sounds enormous. It's a puppy compared to the ones in other galaxies nearby, which go up to billions of solar masses. So here is a flight path for SOFIA that would let somebody take an 8-hour continuous measurement. So you want to know how long SOFIA can point at one thing. Depends on the thing and the season and so on and the latitude that you take off from. But if you take off from New Zealand and head out here and climb to altitude and then look at 30 Doradus, which is a star-forming region, and then take a turn over southern Australia and do this long 8-hour curve and point at the center of the galaxy continuously for 8 hours and come back to Christchurch, which is our base in New Zealand, you can get that long of an exposure on the center of the galaxy. So the base we'll use in New Zealand is the base that supplies the South Pole bases. So we'll just share a hangar with the National Science Foundation's facilities down there. This is basically the first real image that SOFIA took on that first light flight in May 2010. This is Jupiter as seen with a visible light camera almost the same time, like a week earlier, but we timed this so that it was approximately the same face of Jupiter. Here's Jupiter with SOFIA. Now the color scheme is, there's no objective way to represent infrared images to the human eye at visible light wavelengths. You can't see infrared, I can't see infrared, so the person who processed this image made some choices about what he wanted to bring out, and there are other ways to do it. You could do it in a number of ways, but what he's done here, this bright white strip is hot. This is showing you upwelling deep into the interior of Jupiter that's warmer than the cloud tops. And here in the visible light picture, the brown is upwelling of organic materials. That red and brown is organic stuff coming up from updrafts from the interior of Jupiter, And in the infrared picture, we see that it's warm, it's hot. You may have heard that Jupiter puts out twice as much radiation as it gets from the sun. It doesn't come out all over evenly over the planet. It comes out in restricted zones where there are these upwellings. Here's another thing that SOFIA can do that's not infrared. If you have an object in our solar system that moves across in front of a background star, you can do things like measure the size of this foreground object and whether it has rings and whether it has an atmosphere and the properties of that atmosphere by the way it cuts off the light of the background star. You imagine if a planet has a thin atmosphere, then as it blocks the star, it seems to have a soft edge. It doesn't block the light completely instantly, but gradually, and then completely finally. So if we can fly our observatory in the shadow cast on the Earth by this foreground solar system object by the light of some distant star, we can do a lot of science and determine what's going on here. That is a little cartoon of the Kuiper Airborne Observatory. The Kuiper discovered that Uranus has rings by doing this experiment. They were flying in the Indian Ocean. Uranus moved across in front of a star. Just before Uranus covered the star, there were 5 little dropouts. The light was cut off 5 times and then completely went behind the planet, came back out, and then 5 more dropouts. And so, oh, Uranus has 5 rings. And so SOFIA can do this, can go anywhere in the world and be wherever the shadows of these solar system objects are falling. So I was fortunate to be on a SOFIA flight that was measuring this Pluto Occultation. So Pluto moved in front of a star, and here's our flight path. We left Palmdale, we flew out over the Pacific, and you see this little curve here? That was Lowell Observatory taking images of Pluto and the star, sending them to MIT to be crunched rapidly on a supercomputer where they said, oh, the shadow is going to fall 60 kilometers north of where we predicted it yesterday, because Pluto's position isn't that well known. So you have to hold up. Don't go far south as fast as you're going. So we took a little curve here, slowed down, and then headed south. And at this point, Pluto's shadow, which is the size of Australia, because that's how big Pluto is, came across the Pacific at 50,000 miles an hour and went right across us. And we were in the middle of it when the star lit up the atmosphere of Pluto in a ring. And all in that data, in that image, we have the properties, the density and structure of Pluto's atmosphere lit from behind by this star for 7 seconds while we were right at the right place at the right time. There's nobody else with a telescope out here, 2,000 miles west of Acapulco, something like that. You see these images here. This is Pluto, this is the star. 200 minutes before the occultation. Here they have merged to our view. It looks like one object, but they're just not resolved. But here Pluto has hidden the star, and you can tell it's fainter, right? Pluto and the star are about the same brightness, so it went down by about half for a few minutes. And then here is Pluto has uncovered the star, and it's brighter again. And the fact that Pluto has an atmosphere that's measurable is a little bit of a puzzle because it's too cold and it's too small. But we could see the atmosphere, we could measure it in this situation. Okay. Another thing that SOFIA can do by being an infrared telescope, our spectrometers can measure and detect organic molecules. It turns out organic molecules are of a size where their spectral fingerprints are at infrared wavelengths often, many of them. And it may be a surprise, it may not be a surprise, but it may be, that the universe is full of organic, not biological, it's not the same thing, organic, complicated carbon compounds. Murchison meteorite is full of organics. Saturn's moon Titan's atmosphere, that reddish-brown color, the particles in a comet's tail. And here is one of my favorite pictures. This is Saturn's moon Enceladus, and this is a several hundred kilometer tall geyser of salt water with organic compounds blowing out the side of Saturn's moon Enceladus. Wonder what's going on there. Somebody's not happy. Actually, it's being tidally heated, squeezed by Saturn, heated from the inside, so the geyser is just from perhaps an ocean of water under an ice crust that's coming out through fissures. But organics are verified because the Cassini probe went right through that plume and made some measurements. And other contexts, this is a star-forming region, and that brownish color, that's organics. And here's a galaxy, Messier 81, and the filter with which Spitzer took this picture is tuned to see the radiation from a particular kind of organic molecule called PAHs, and they're all over in the spiral arms, which is where stars form. Actually, the spiral arms of a galaxy tell you where the star-forming process is going on right now. Spitzer took this picture, and it's beautiful. We have a 3 times larger telescope, so we can see 9 times more crowded, 3 times better detail in 9 times more crowded regions in this galaxy than Spitzer could. And we come home every morning, and we're going to last 20 years, and Spitzer did a heroic job and lasted 5 years until its cryogen supply, liquid helium, ran out. We don't have that. We're not chilling our telescope. We're chilling the insides of the instruments, but our telescope is at stratospheric temperature, 40 below zero, but it's not cooled. All right. So there's a punchline here about organics. We see organics everywhere in the wider universe. We see organics in several contexts in our solar system. We see them on Earth, of course, plenty here. We don't know if those 3 organic reservoirs are connected or not. We don't know if the interstellar organics join the solar system and then end up on the planets when the planets form, or if the Earth's organics are all homegrown, or somewhere in between. And that's one of the things that SOFIA can do by measuring the isotope ratios of the organics in all these contexts. Are they connected, or are the organics completely separate shows in each of these places? Okay, so I'm almost done here. This is, we had Airborne Astronomy Ambassadors Program. Actually, let me flip to the next slide, which is maybe a little, oh, well, this one has a little better explanation. From the time that SOFIA was envisioned, NASA, some enlightened NASA, especially enlightened NASA officials, said, you know, you can have an amazing program where citizens, teachers, journalists can fly on your observatory. Can't do that on Hubble. So SOFIA was designed from the start with a console that's designated for teachers to fly on the plane. That's the Airborne Astronomy Ambassadors Program, and it's my delight to be managing that program among my other duties. So the first group of 6 teachers we flew in summer 2011, and I and 2 of my staff members were the escorts for the teachers. This is Terry Herder. He's a professor at Cornell who built the forecast camera. He has a very large brain. So here, Mary from Virginia, Chris from Michigan, and Peggy from Illinois. This is Marita from San Jose at the far left, and Terry from Wisconsin, and this is, how come I can't remember? Oops. All right, well, the 6 of us, the 6 teachers, each with a flight escort, flew in 2011, and we are now getting ready. And also 2 German teachers with their escort went on board in 2011 as a pilot program for this. Our plan is eventually that we'll be flying 50 teachers a year, and not as a joyride. The idea is that they'll be trained to understand what one particular scientific mission is trying to accomplish. They'll have been talking to the astronomers for months ahead of time, teleconferences and web conferences and on email. And then on board can be junior partners helping with the observations. and then go back to their school districts and their communities and use this to enhance the STEM education, science, technology, engineering, and math in communities across the country. So we have 26 of them selected now in the first batch, first full year's batch, and 4 of them flew 2 weeks ago, and the other 22 we're going to take up in the remainder of this year. And these are all, I have to tell you how wonderful it is to be working with these vital, energetic, dedicated teachers who are going to find a way to take their SOFIA training and tell people how science really works. It's not this nice loop from hypothesis to experiment to hypothesis to experiment. It's blood, sweat, and tears most of the way around that circle, and they know that. They've watched it. They've been on board SOFIA while the astronomers were sweating and nothing was working, and so on and so forth. That's how it really is up there. And if we get our wish and we get 20 years of SOFIA funded and fly 50 teachers a year for most of that, then everybody in the country will know somebody who knows a teacher who's been on SOFIA. And I think that the impact is potentially enormous, not of a completely different flavor than Hubble, of course, which is the People's Telescope, and people went to bat to save Hubble. And the Mars rover, everybody has a soft spot in their heart for Mars rovers, but we're hoping that people will know in a few years that SOFIA, oh yeah, my cousin's teacher went on that airplane and helped astronomers do what they're doing. And so, the applications for Cycle 2 opened last Friday. So if you go to the SOFIA website, we take groups of 2 teachers, so we need a team of 2. One of them has to be a middle school or high school science teacher. The other can be any grade, any subject, and could be an educator in a museum, not necessarily a classroom teacher. So teams of 2, one of them is the anchor member who's a middle school or high school teacher. We pay the load, we pay your full freight, we pay for your substitute, we work to connect you with the astronomers, we support you to carry out your proposal after you're back on Earth for a year. And so if you have friends who are teachers, or you're a teacher, or family members who are teachers, you could look at our website here. Just do a search on SOFIA and disambiguate the capital of Bulgaria, and basically you'll get to us. But this part of the SOFIA program, the education part, is run by the SETI Institute and the ASP, which are also sponsors of this lecture series. And the ASP is having a national conference on educating the public about astronomy this summer in mid-July. And some flyers for that are on the table. I put them out as I came in the door. So here's SOFIA, the Science Center. It's not a NASA address. This is the Science Center, which is an academic institution.edu. There I am, and I do parties. Actually, if somebody wants to invite me to their classroom and it's within driving distance here, I'm delighted to do that, any grade level. I think this material is over the tops of the heads of like little ones. I'm remembering being in a 3rd grade classroom and a student asked me, "Why is Uranus a Greek name and the other planets are all Roman?" Oh yeah, well, so let me get back to you on that one, and also a 4th grader who asked me what spectra of Jupiter's great red spot showed it was made out of. I thought, I hope I got tenure by the time you're looking for a job. But anyway, so I'm not shy at all about 2nd, 3rd, my granddaughter's kindergarten class. I do that too, several times. And so the Spitzer Space Telescope's award-winning infrared tutorial, award-winning in terms of its graphics quality and so on, is you can find it by looking for Cool Cosmos. It's hosted at Caltech, And so this is little movie clips of infrared camera goes to the zoo, infrared camera in your kitchen, infrared camera in your backyard, those kinds of things. And also you can get how to make, for the teachers in the audience or people with young ones, you can, with an Edmund Scientific prism, a couple of thermometers, and a shoebox, you can redo Herschel's experiment and show that the infrared is detectable in the sunlight. So I think that's what I have, and at the time is 8:17, and it took us a while to get started, but I like questions, and I'll take them as long as you want to throw them at me. So thank you.
It looks like you take photographs and you also take spectra of things. And I'm wondering what the resolution is in terms of in your photographs of your spectra. Do you have to use all the energy coming in to do the spectra, or can you get a spectra at what would correspond to one point in one of the photographs?
Yes, so the question is how small a region of something that you're studying can you take a spectrum of? And it's that we have 3 spectrographs, and the answer is a little different for each of them. But yes, you can take, it's just one, you can get a spectrum of one pixel, one picture element. So let's say SOFIA's spatial resolution, you can get like 10 spectra across Jupiter, for example, something like that.
And the spectra simultaneously?
No, we can't put 2 instruments on at the same time. So if we're going to have a flight that's got the camera on, then we come down, take the camera off, and put the spectrograph on. So that would have to be 2 different flights. But someone could propose, I need a spectrum and I need a picture, so then they'd get 2 flights. Right?
Okay, so you actually have to do the spectra pixel by pixel, basically.
Yeah, well, the spectrograph has an entrance slit, so it covers sort of a rectangular piece of the sky, so you get that direction a fair amount of sky, but you can get several resolution elements along the slit, right? Yeah, I hope that. Yes, sir.
So what is the connection between infrared and heat? It seems to be used kind of interchangeably, and I'm trying to understand that.
You're right. The term infrared radiation or heat radiation, they're usually used as synonyms when you are holding your hands out to get warm by a fire in a fireplace. That's infrared radiation that is warming you up. But the technical term heat refers to the energy content of an object in the form of the agitation of its particles. So a hot thing can give off radiation, and you can receive that. So that's a form of light given off by an object. So I think some of that comes from the idea that an object that's warm enough to give off heat, give off infrared radiation, but not warm enough to give off light, you're getting infrared, and you're getting, you can call it a hot or heat radiation. So here's an example. Look down into your toaster, start the toaster. You don't see anything. Then for a while, after a while, the toaster coils start getting orange, and then they get orangish yellow, and if you put on a lot of voltage, you'd get them yellow-white, and your toaster would melt, right? So, but while it's warming up, but before you can see anything, it's making a lot of infrared radiation and not much visible light. So something at a temperature of 500 or 1,000 degrees, it's giving off all infrared light and no visible light, and I think that's where that comes from. That makes sense.
Thank you, Dr. Backman, for your talk. What kinds of technology are the detectors in SOFIA using?
They are solid state. At each wavelength band is a different substance that's the optimum detector. So, but they're, for instance, flight cam, the UCLA is indium antimonide is the substance that's the pixels.
Are they bolometers then?
None of these are bolometers. They're all photovoltaic, except the great instrument, which is basically a short wavelength radio receiver. So they're all photon detectors and not bolometers, except great, which is basically a radio receiver.
And did I understand correctly that you don't cool the optics below the ambient at the stratospheric
Right. The
altitude?
telescope mirrors are at stratospheric temperatures. The insides of the detectors are at liquid helium temperatures, but the telescope is at stratosphere temperature.
Thank you.
Right. Yes.
I presume that your mission is pretty budget efficient for the kind of science you're doing. I just wondered if you could give us some flavor of that compared to satellite type technologies. And also, separate question, but I've heard far infrared and near infrared. I was wondering if maybe you could kind of explain the difference in utility.
I'll go
of that.
the second one first. The near infrared means wavelengths that are closer to visible light. And far infrared means it's longer wavelengths, more distant from visible light. So near infrared, you could say, is almost visible light, and far infrared is. And your other question about the funding, our total budget for a year's operations is $85 million, which sounds like a lot, but that's 85 cents per family, right? And that is the 80% U.S. contribution. So Germany is putting in 20 million. So it's 100 million. It's Hubble's budget for a year is 300 million. So we're the U.S. part of Hubble is about 3 times the U.S. part of SOFIA. But the total development cost, if you include the space shuttle missions up to, turn some wrenches on Hubble. I think it's about 5 or 6 billion, and in a total lifetime of Hubble costs are about 6 billion, I think, and SOFIA's will be 2 billion. So again, it's about a ratio of 3. So that's 20 years of us and 20 years of them for about a factor of 3 difference.
At what altitude are you flying at?
We're operating at 41 to 45,000 feet, which if all we need to do is get above the tropopause, and that's different height at different, over the continents and over the oceans is different altitudes. But 45,000 is the highest that we've gone, and we're not challenging the ceiling for a 747. 747 could go higher than that, but we're like 10% above the altitude of commercial flight. So we don't mix it up with air traffic control and commercial flights. We're above the commercial flight layer once we're operating. So we just go wherever we want.
You have a large object that's going through cycling through, I guess, room temperature to minus 40. Have you run into any interesting things happening to the object, and how long does it take for it to finally stabilize at altitude?
That's a great question. So the question is, your telescope mirror is at 10 or 20 or Palmdale 50 centigrade when you take off, and then you're going up to minus 40 centigrade. We take an hour to get to altitude. We could climb faster than that, but we take that time to let the telescope equilibrate, and then we're eventually going to install a liquid nitrogen system in the back to chill the framework of the telescope, not so it operates cryogenically, but so it gets to stratospheric temperature faster. So we're just not trying to go below stratospheric temperature, just try to get it cold.
Anything weird happen with the mechanics, like things breaking or cracking?
No, that's it hasn't been a problem. We're concerned that if we come back down too fast, that and the mirror is still cold. And we have a system to blow dry nitrogen in there. Otherwise, we're worried that we'll get condensation on the mirror. But all the telescope systems are happy cycling from plus 20 to minus 40 and back. I wouldn't be, but there you go.
How can SOFIA participate in the SETI program?
In the what?
The SETI program. In search for.
You wonder why SETI's got any connection. It's because Edna DeVore, who ran the teachers on the Kuiper program and put what is the head of education, and so for the SETI Institute. So we're not contributing to that effort, but the SETI Institute is, half of it is a federally funded research institute for astrobiology research, and organic chemistry in space is one of SOFIA's sweet spots. So there's a connection there. SOFIA's not going to detect the alien signals, but we can talk a lot, I think, in a few years about the organic chemistry of the interstellar medium, for example. Yeah. Okay.
Thinking about that particular image of that accretion disk around the black hole at the center of the galaxy, is SOFIA able to do any radial velocity measurements?
Yes. Right, our spectrometers can get the velocities of that material easily. Yep.
And has that been done, and is it published somewhere to get an idea?
Let's see, the only data we've taken on the center of the galaxy so far was with the forecast camera. So but this summer in July, it's the German spectrometer GREAT that's going to go down to New Zealand, and the center of the galaxy is up in July. So I bet they'll be doing that. The velocities of that material, which is 3 or 4 light years away from the center, is not that outrageous. It's a few hundred kilometers per second, and that's been measured, published, some of it's measured from the Kuiper Airborne Observatory. So the speed of stuff in that ring, it's published. Let's see if I can remember it. Genzel is a first author, Genzel. So if you do a Google search on a publication by Reinhard Genzel, you can find those measurements.
Thank you.
No. Sorry.
I thought I had heard that tracking near-Earth objects was done in the infrared to pick up their heat, and I'm wondering, is SOFIA applicable to that effort?
Potentially, yes. A near-Earth object that's sort of Earth temperature would be putting out a lot of infrared relative to the small amount of light that it's reflecting of sunlight. So actually infrared detectors are the best way to find small near-Earth objects, and the telescope can track them. And we actually did have a proposal for this year's observing for somebody who wanted to give a pilot program to look for near-Earth objects, or look at ones already known, not do a survey. We're probably not the best instrument to do a survey, but we're certainly the right one to do a follow-up on objects discovered by other means. So it's one of the science topics for SOFIA, yes.
All right, last question.
Okay, I don't know if I answered that completely though, sir. Yeah, okay.
So if you can think 20 years ahead, what do you expect to be the greatest things that you think this telescope can discover in those 20 years?
Now, I wish I could. I'll give you the example. I has a minor connection to the Spitzer, the small infrared space telescope, and they had years and years of justifying Spitzer as here's the list of things that Spitzer will investigate and will do better than any other observatory to find out. And the things that Spitzer actually did once up was a completely different list, right? So which is good. Right? So I wouldn't want to venture it because I'm going to be wrong if I try to guess what. So your question could be rephrased as 20 years from now, what will SOFIA be famous for? And I'm glad that I can't guess. Right? I think some of this organic chemistry of the interstellar medium, that's pretty cool, but we're going to try an experiment on April 30th of watching hot Jupiter, a big extrasolar planet close to its star, cut in front of the star and try and get a spectrum of the atmosphere of the planet as the starlight shines through it. It's been done with Hubble, but we're going to try and see if we can do it and do better with a higher resolution spectrometer. So, that's stuff just in the next 6 months. I don't know what 20 years will bring. But the thing about SOFIA, I'm going to get back on my soapbox, we can have 3 or 4 generations of instruments as the solid state physics of the detectors gets better. So the detectors, so the telescope won't get bigger, but if you have 100 times better detector 15 years from now, it's like having a 100 times bigger telescope. You know, so that's one of the things about SOFIA. You don't have to send a crew up to pull out the old ones and pop in the new ones. Just build them here and put them in. Right?
Thank you.
Yeah.
Well, we'll ask you back in 20 years and see what you say.
Right.
Let's thank Dr. Backman.
You're welcome. Thank you.
And we'll welcome everybody else back April 17th for brown dwarfs and May 15th for Mars. Drive safely and have a good night.